What if I told you that some of the universe's biggest secrets lie hidden in equations and numbers, still unsolved, still waiting to be deciphered? Through the corridors of time, these mysteries have beckoned the greatest intellectual pioneers, offering glimpses into the profound depths of both mathematical and physical realms. From the swirling dance of fluid dynamics to the enigmatic distribution of prime numbers, these challenges defy simple understanding, yet promise revolutionary breakthroughs. Today, we delve into 5 of these enigmatic puzzles, each holding the key to profound insights in science and mathematics. Imagine trying to predict the unpredictable, like the chaotic dance of smoke or the swirling fury of a tornado. At the heart of these phenomena are the Navier-Stokes equations, a set of partial differential equations that describe how the velocity field of fluid substances, such as air and water, evolves over time. These equations are pivotal in understanding everything from ocean currents to blood flow in our bodies. However, while the Navier-Stokes equations are incredibly powerful, they come with their own set of challenges, especially when it comes to turbulent flows. Turbulence, with its unpredictable and chaotic nature, makes modeling a highly complex task. This is where mathematicians and physicists hit a wall. The equations become notoriously difficult to solve in these conditions. Solving these equations completely could revolutionize numerous fields, including meteorology, engineering, and even medical sciences, by providing more accurate predictions of complex fluid behaviors. As it stands, the full mastery of these equations remains a turbulent quest in the mathematical community. In 1859, Bernhard Riemann proposed an idea that would become one of the most tantalizing unsolved puzzles in number theory. This idea, known as the Riemann hypothesis, suggests a profound order in the distribution of prime numbers, those indivisible numbers greater than 1. It centers on the behavior of the Riemann zeta function, a complex function that encodes deep insights into the distribution of primes. The hypothesis posits that all non-trivial zeros of this zeta function lie on a critical line in the complex plane. This might sound esoteric, but its implications are vast. A proof would provide a master key to predicting how prime numbers are spread along the vast tapestry of integers, impacting cryptography, computer science, and numerical analysis. Despite numerous attempts by some of the sharpest minds in mathematics, the Riemann hypothesis has withstood over a century and a half of scrutiny. Solving the Riemann hypothesis could potentially rewrite the mathematical rule book on primes, yet it stands resilient against time and trial. In our digital world, the boundary between the possible and the impossible is defined by one of the most profound questions in computer science. Welcome to the enigmatic universe of the P versus NP problem. Introduced in 1971 by mathematician Stephen Cook, this problem asks a tantalizing question. If a solution to a problem can be verified quickly using a computer, does that mean the problem itself can be solved quickly? The implications of this question stretch far across the computing landscape, influencing fields like cryptography, where the security of our data often depends on certain problems being hard to solve. In algorithm design, a resolution to P versus NP could revolutionize how we approach everything from scheduling to data analysis. As one of the 7 Millennium Prize problems, solving P versus NP carries not only a $1 million prize, but also the potential to reshape technology as we know it. Whether every problem with a verifiable solution can also be solved quickly remains a digital dilemma of monumental proportions. Dive into the quantum realm, where the very fabric of reality behaves unlike anything we experience in our everyday lives. Here, we encounter the enigmatic world of Yang-Mills theory, a cornerstone of modern physics that dramatically extends our understanding of fundamental forces. At its core, Yang-Mills theory describes how particles like quarks and gluons interact within the nucleus of an atom, governed by the strong and weak nuclear forces. One of the most perplexing aspects of this theory involves the mass gap. This term refers to the phenomenon where particles, despite the force carrying particles theoretically being massless, exhibit non-zero mass. The existence of a mass gap is crucial because it explains why these particles do not travel at the speed of light, and instead have tangible, measurable masses. Understanding why this mass gap exists is vital. It links directly to our comprehension of particle confinement and the stability of matter in the universe. The solution to the Yang-Mills and mass gap problem holds the promise of advancing our comprehension of the universe's building blocks. Hidden within the elegant curves of elliptic equations lies a secret waiting to be solved. The Birch and Swinnerton-Dyer conjecture, a fascinating puzzle in number theory, proposes a deep connection between the number of rational solutions on an elliptic curve and certain properties of its L function. This conjecture has been partially proven for many curves, yet a universal proof remains just out of reach. As researchers dive deeper, they uncover more about how geometry and algebra interlace through these complex relationships. This conjecture connects the dots between geometry, algebra, and number theory, challenging our understanding of these mathematical landscapes. Our journey through these mathematical mysteries shows a landscape rich with intellectual challenges and opportunities. Each problem, from the swirling complexities of the Navier-Stokes equations to the enigmatic patterns of the Riemann hypothesis, beckons the keenest minds to delve deeper. The pursuit of answers in the realms of P versus NP Yang-Mills theories and the Birch and Swinnerton-Dyer conjecture is not merely academic. It's a quest that fuels technological breakthroughs and deepens our understanding of the universe. As we push the boundaries of the known, each unsolved problem is not just a challenge, but an invitation to explore, discover, and perhaps to revolutionize our world.